Isotopes in medicine. Radiation in medicine is mainly used for destroying cancerous cells and for tracing what is happening within the body. Radiotherapy involves directing radiation from outside the body towards cancerous cells. As the radiation must penetrate the body, gamma emitters are used, and as the radioactive source itself does not enter the body, just the radiation it emits, long half-lives are preferable. This reduces the need for regular replacement of the sources. For tracing, a radioactive substance itself is placed inside the body, and its location monitored from outside. Again, a gamma source is used, so it can escape from the body, but now the half-life must be long enough to complete the procedure, but short enough to decay quickly and not leave the patient radioactive for too long. Iodine is used within the body almost exclusively by the thyroid gland. The isotope iodine-131 is radioactive, emitting beta and gamma rays, with a half-life of 8 days. It can be used for treating hyperthyroidism and thyroid cancer, and can be also used to check the function of the thyroid gland. Technetium-99 is produced when molybdenum-99 decays, and it can be washed out of molybdenum oxide using a salt solution in a machine which is called a technetium generator. This means a hospital can have a ready supply of technetium-99. Technetium-99 is what is called metastable, meaning it remains in an excited state for a relatively long time. It has a half-life of 6 hours before it emits gamma rays to become the normal form of technetium-99. When it emits the gamma rays, it turns from what is written as technetium-99m to technetium-99. The gamma rays are relatively low energy. This makes them less damaging to the body than higher energy gamma rays. The next decay in the series is to ruthenium. This involves beta emission, which could be dangerous, but with a half-life of 200,000 years, this means very few beta particles will be emitted, meaning little exposure to the patient. Technetium-99m is mainly used as a tracer. It's injected into the body, attached to different compounds used by particular parts of the body under investigation. Its position can then be monitored from outside the body. Positron emission tomography, or PET scanners, usually use fluorine 18, which is a positron emitter. It undergoes beta plus decay. The fluorine is attached to glucose, and this is used all over the body. When a positron is emitted, it will immediately meet an electron within the body. They annihilate each other and release 2 gamma rays. These must travel in opposite directions to conserve momentum. The time difference in the detection of these 2 gamma rays allows the precise location of their point of creation to be found. This allows a 3-dimensional image of the body to be created, and can highlight things like tumours where extra glucose is being used. This simple diagram shows how the process works. Gamma ray detectors will be located in this ring all the way around the body. This shows a cross-section of the body, and the body will be moved towards us and away from us, passing through the detectors. There are of course electrons throughout the entire body, and here we have a fluorine 18 atom. This undergoes beta plus decay, changing and emitting a positron. This positron will immediately meet an electron. They annihilate each other and release 2 gamma rays. This gamma ray has had slightly shorter distance to travel to reach the detector than this one, so the computer will know that the fluorine 18 atom was located somewhere on a line between these 2 detectors, and knowing the time difference in the arrival of the gamma rays, we'll be able to pinpoint it to this precise location. Many hospitals will now have their own particle accelerators on site. This is used for producing isotopes with very short half-lives, making them expensive to store and transport. If you're using a substance with a half-life of 24 hours, for instance, store it for 1 day, and you have half of what you started with.